Ever wondered how Siri or Alexa picks up your voice commands? Well, in this video, we're going to be going through exactly that. In this video, you're going to learn how to build your very own deep audio classification model using Tensorflow and Python. Ready to do it? Let's get to it. So we're going to be going through a ton of stuff. And as per usual, all the code for this is going to be available in the description below via GitHub, and I'll also throw a link up on the screen right about now. Now, what is it exactly that we're going to be doing? Well, we're going to be working with audio data. So first up, what we're going to need to do is learn how to take that audio data and bring it into Python into a numerical representation. We're then going to transform it a little bit and convert it into a spectrogram. So this means that we can use convolutional neural networks to be able to process that and classify it. And we're also going to perform sliding window classification. So we're actually going to take a larger audio clip and be able to count the number of specific detections within that clip. So this is particularly useful if you wanted to do something like speech command recognition later on. Now, in terms of the data that we're going to be using, we're actually going to be competing in the Z by HP Unlock Challenge, but more about that later. Let's go and jump right into it. Now, as part of this journey, we're going to be speaking to our fictional client, Damone, along the way. This is going to give you a little bit of context while we're building the deep learning model. Let's go and have a chat. Sup, Nick? Heard you're going to be helping us out with that audio analysis problem. We're trying to classify capuchin monkey density in the rainforest using audio clips. Interesting. Yep, I'll be giving you a hand, Damone. You sent over that dataset yet? Should be on Kaggle now. Perfect, I'll check it out. So, what are you going to be getting up to first? First up, we're going to need a way to numerically represent the audio. We should be able to do this using the Tensorflow audio processing libraries. Nice, good luck. So let's run through the breakdown board. So first up, Damone is going to send us some bird call clips. That's the best bird that I can draw. And these are going to be roughly 3 seconds in length. So each bird call that we're going to try to detect is going to be 3 seconds. We're then going to take that particular set of bird calls and load it up into Python. And in terms of how we're actually going to do that, we're going to take it in and read it in as a waveform. So this is going to be done using the TensorFlow package. So what we'll actually get out is a waveform. Now, from that waveform, what we actually want to do is convert it into a spectrogram. So the reason that we're going to do this is it's going to allow us to use computer vision techniques like convolutional neural networks to be able to perform that classification. So we'll take our raw waveform, and what we're going to do is convert it into a spectrogram. And you'll actually be able to see what the capuchin bird waveform actually looks like through that spectrogram. It's actually really, really interesting. So once we've got that spectrogram done, the next thing that we're actually going to go on ahead and do is push this into our convolutional neural network, which will be built using TensorFlow. And the output that we're actually going to get from that neural network is just going to be a binary outcome, so 1 or a 0. Now, that 1 is going to represent whether or not we've actually heard a capuchin bird within that particular clip. The 0 is going to represent the fact that we haven't. So the output of our neural network is going to be either a 1 or a 0. Now, the thing is, the final outcome that Damone wants to get to is the density of bird calls within a particular audio file. Now, the final audio files that we're actually going to get from Damone are actually going to be slightly longer. So rather than just being 3 seconds, they're actually going to be 3 minutes each. So if we visualize our full clip as this entire time period, so 3 minutes, what we actually need to do is slice that clip into different segments. So we're actually going to call these segments windows. So we're going to slice them in to 3-second segments, so on and so forth. And then we're actually going to take our TensorFlow neural network, which has been trained on 3-second bird clips, and we're actually going to slide it across each one of these windows. And once we've got these classifications, all we really need to do is count the number of calls that we've heard. So if we hear a call here, that'll be 1. If we hear a call here, that'll be another one. Or in this particular case, if it doesn't hear anything, that will be a negative call. Now, what we'll actually notice later on is that we'll get consecutive calls or consecutive detections which are counted as individual calls. We'll actually group these up so that if we hear consecutive calls, we're going to actually aggregate these and consider them as one. So in the end outcome, we'll be able to push out a CSV with all of Damone's outputs. Let's jump to it.
Alrighty, so we're going to go on ahead and build our audio classification model for Damone and the team. Now, in order to get started, the first thing that we're actually going to need is some data. So if we jump on over to the associated Kaggle repository available, or the link will be available in the description below, what we're going to find is a whole bunch of information about the actual challenge. So this is what we're going to be able to, or what we're going to be trying to classify, the capuchin bird. Now, the challenge specifically is to build a machine learning model and code to count the number of capuchin bird calls within a given clip. Now, specifically, the data that we're going to be using, if we scroll on down to the Data Explorer, we are going to get 3 different folders. So we're going to get forest recordings, which are the full clip that we need to pass through and count the number of calls through. We're going to get some specific capuchin bird call clips, which are about 3 seconds each. And we're also going to get a set of files which are not capuchin bird clips or not capuchin bird calls. Now, what we need to do is download this data. So if you jump on over to the Kaggle repository, which has been created by none other than Ken G, and hit download, this is going to download the data set as a zip archive. Now, once that's downloaded, what I want you to do is grab that data and bring it into the repository that you're working through and put it into a folder called, where are we? Audio classification, and put it into a folder called data. So you can see I've got forest recordings, past capuchin bird clips, and past not capuchin bird clips. So if this is the main folder that you're working in, create a folder called data and then throw those in there. So we'll have 3 different folders inside of that data folder. Now, the next thing that I'm going to show you is where to get this code. So if you want to follow along, all you need to do is go to github.com/nicknocknack/deep audio classification, and you're going to have the Jupyter notebook down there, as well as a example results CSV that you'll be able to work with. Now, the end goal is to produce a CSV that will then be able to submit to the HP Unlocked challenge. So if you go to hp.com unlocked, this is going to take you to this page that I'm currently looking at. Now, the cool thing is that there is this interactive movie that you're able to watch and see how we're actually able to use data science in the real world. So it's pretty cool what you can actually get up to with it. My mouse is lagging now. So if we take a look at that and you scroll a little bit further down, the challenge that we are going to take part in is challenge 3. So if we step into challenge 3 and have a quick read. So this is what we're trying to do. So Michaela is helping, no, that's the data visualization one. Let's go to challenge 3. Challenge 3, right over here. All right, cool. So what we're trying to do, so Michaela, Damone, and Eva need to pinpoint the place where a certain bird population is most dense. This is a critical point in their journey and the clock is ticking. Use your data science skills to analyze these audio files and identify the areas of the forest that have the greatest density of capuchin birds. Remember, Ken G and me are here to help you with the tutorial walkthrough if you need a little assistance. And when you're ready, submit your answers in the form below to continue your journey and enter into the sweepstakes. So if you scroll on down, once you've gone and completed the challenge, what you can do is just select your results file, throw that up, and then fill out your details. And you can actually enter the challenge and go into the draw to win 1 out of 10 HBZ Book Studio notebooks and a potential trip to the Kaggle Days Championship in Barcelona, which would be absolutely awesome. I'd love to go. All right, but now we've taken a look at what we need to do. Let's actually jump on over into our Jupyter notebook. So I've got the notebook from the GitHub repository, which is audioclassification.ipynb. If we take a look at our folder structure, I've got all of my audio clips inside of a folder called data, and then forest recordings, and then we've got the capuchin bird clips and past not capuchin bird clips. So let's have a quick listen to some of those first up, just so we know what we're actually working with. So I'm going to go into that folder. And let's play one of these files. So this is the forest recording. So it's going to be the full clip. So you can see it's about 3 minutes long. And we've just got some audio of the forest. So we're going to be trying to pass through this and count how many capuchin birds we actually hear. That's a capuchin bird right there. So ideally you'd count one there and you'd keep counting as you actually go through this clip. Now, if we take a look at the training data that we've got past capuchin bird clips. So if we play one of these, so that's a capuchin bird, about 3 seconds. If we take a look at the not capuchin bird clips, Just got some like crickets or some bird songs out in the forest. And again, those are about 3 seconds. So cool. All right, so what we're going to first up need to do is take those capuchin bird clips, the 3-second clips, and convert them into a waveform. So this is going to take the audio and convert it into a tensor. Now, in order to do this, the first thing that we're going to be doing is importing and installing some dependencies. So the first thing that we'll do is we'll install some dependencies. In order to do this, we are going to be running !pip install TensorFlow, which is going to install TensorFlow. It's also going to install TensorFlow-GPU. This is particularly useful if you've got a CUDA-enabled GPU. We're going to be installing TensorFlow-IO, so that's going to be useful for audio processing, and matplotlib to visualize our results. So if we go and run that cell, that should go on ahead and install our dependencies. I've already got them installed, so it's gone relatively quickly. Let's just double check there's no errors there. So that all looks good. Cool. So now that we've got our dependencies installed, so we've gone and run this one line, the next thing that we can go on ahead and do is load up our dependencies. So there's going to be 4 specific dependencies that we're going to be bringing into our notebook. So the first one is OS. So in order to do that, we've written import OS. And this is just going to make it a little bit easier to traverse through directories. So our data is going to be stored inside of that data folder. So we're going to need to go into data, and then we're going to need to go into past capuchin bird clips and then past not capuchin bird clips. So OS just makes it a little bit easier to navigate through that. Then we've written from matplotlib import pyplot as PLT. So this just makes it easier to visualize our results and our waveforms once we've gone and converted our audio. I've then brought in TensorFlow, so import TensorFlow as TF. So we're going to use TensorFlow a little bit later on to actually build our deep learning model. And then we've brought in TFIO. So import TensorFlow_IO as TFIO. So that just makes it easier to process our audio clips and convert them into a format that we're going to be able to use. So if you just select that cell and run that cell, that should load in our dependencies. Now that is step 1 now done. So import and install our base dependencies. So we've gone and installed some, and we've also gone and loaded them into our notebook. The next thing that we need to do is actually build our data loading function. Now the first thing that we need to do there is define our paths to our files. So this is relatively straightforward. So we're just going to test out a single file to begin with. So first thing we've defined here is the path to a specific clip. So capuchin_file equals os.path.join. And then the path to that is data, comma, past_capuchin bird clips, comma, and then I've picked a specific file. So xc3776-3.wave. So if you actually just take a look at that, let's actually run this. And if we type in capuchin file, all we're really getting there is a file path. And this is where OS just comes in handy. So whether you're working on Linux or whether you're working on Windows or Mac, it is going to work out the appropriate way to define a file path to a specific file on your operating system. Then we've defined one for our capuchin, or an example of a capuchin bird. And then we've also gone and defined one for a not capuchin bird. So for our not capuchin bird, the file path is os.path.join. And then we're going into our data folder again, because remember, we've got everything stored in there. And then we've gone into past_not_capuchin bird_clips. And then we're grabbing this one here. So afternoon-bird song in forest-0.wav. So if we take a look at that one, so not_capuchin bird file, this is the file path to that specific file that we're going to be using there. Okay, so that's the path to our initial file. And remember, this is just a single file at the moment, just to test out when we actually go and load in our data. Then what we're going to do is we're going to set up our data loading function. And this is it here. Now, this is actually adapted from the data loading function that's from the TensorFlow documentation. So this just makes it super easy to actually go and process your audio. I've just added in a couple of comments to basically explain how this is actually working. All right, first thing, so we've defined a new function, so def load_wave_16k_mono. So we are going to be processing our audio file and converting it to 16 hertz, and we're going to get a single channel, so it's going to be mono channel. Now to that, this function is expecting the file name or file path to the specific file that we want to read. Then we're able to load it in and convert it to a waveform. So file_contents equals tf.io.read_file. And then to that, we're actually passing through the file path. So once we've actually got that, we're going to get a byte encoded string. So this isn't actually going to return back the audio yet. It's just going to be a string if you actually go and run that individually. So if I went and grabbed that, Pasted that there and grabbed in our Capuchin file. So you're not actually going to have the audio yet. It's just going to be this. Oh, well, this is the audio, but it's a string here. So that is the decoded version of our wave file. The next line is what actually goes and decodes our wave. So to do that, we've written tf.audio.decode_wave. And then to that, we pass through this byte encoded string and we specify that we only want one channel. So rather than having the stereo audio, we're going to be getting mono audio. This just makes it a little bit easier to process our audio later on. And then what we're going to get out of that is the actual wave file itself and the sample rate. So if we grab that line, paste that here, let's actually take a look at it. If we take a look at the wave, so what you're actually getting back is a tensor of the shape 132,300 with one channel. So this means that you've just got the representation or the amplitude of the wave, which we'll be able to visualize in a second. Then what we're doing is we're squeezing it. So we're getting rid of this trailing axis. And to do that, we've written tf.squeeze, and then we're casting our sample rate to an integer or a 64-bit integer. So this means that we're going to have it in a format that we can then use to resample. So right now the sample rate, so let's take a look at that, is at 44,100 hertz. So, or 44.1 kilohertz. So this means that that is the frequency of the wave that you're actually getting back, or the amplitude of the wave. So what we actually want to do is resample that to be a 16,000 hertz example. So in order to do that, I've written wave equals tf.io.audio.resample. Sorry, I haven't written it. This is actually from the TensorFlow website. So wave equals tf.io.audio.resample. We're passing through the wave from here. So this is once we've got our trailing axis removed, and we're passing through our input sample rate. So this is what it is currently at, which is 44,100 hertz, and we're converting it to 16,000 hertz. So that should effectively reduce the size of our final audio. So if we actually take this, paste it down here. So let's just quickly take a look at the length of this wave file at the moment. So it's 132,300 values. Now, if we go and resample it, so we're going to convert it from 44,100 to 16,000. If we take a look at the size of the wave now, it is now 48,000, so significantly smaller. So this effectively gives us less data that we're going to need to process. Cool. Now, all of that is inside of a function, so we don't actually need to write those individually. All we need to do is pass through the file path to this specific file, and we'll have our pre-processed wave file that we'll be able to work with. So let's get rid of this temporarily, so we don't need that, or that. And then what we're going to do is we're going to plot our wave. So we're first up going to load in our Capuchin file and our not Capuchin file using this function here. So load _wave _16k _mono, and we should get back our wave file, which is at 16,000 hertz for both our valid example, or our positive example, and our negative example. So I've just called them wave and n wave. So if we go and run that, and we actually need to go and run our function. Those are our two waves. And if we go and visualize them, those are our two waves now visualized. So the blue wave is actually that'll be our Capuchin bird. So you can see that you've got that warbling, and our orange line in this particular case is our not Capuchin bird example, or our negative example. Cool. So that is our audio now processed. So we've now, or at least we've gone and processed one sample. So right now, what we've gone and done is we've gone and installed and imported our dependencies. We've also gone and built a data loading function to remember load _wave _16k _mono, and then we've gone and visualized them. So we've got an example of what a Capuchin bird sounds like and what just the generic forest or other songbirds sound like at the moment. Let's jump back over and speak to Damone and give him an update on our results.
All right, Damone, so the first phase is done. We've got the audio in a format that we can work with now. There's one last tweak that we need to do before we get to modeling though. Ah, cool. What's the last tweak? We're actually going to convert the raw audio waveforms that we had by loading it in using the TensorFlow decode wave method into a spectrogram using the short time Fourier transform. You mind dropping the jargon for me? Yeah, my bad, man. We're going to convert the audio wave into what's effectively an image representation. This means that later on, we'll be able to use image classification techniques to count the Capuchin density. All right, shoot me those spectrograms when you're ready.
Alrighty, so spectrogram. So we've now gone and converted our data into a waveform. We've got it inside of Python, or at least we've got 1 or 2 examples inside of Python. What we want to do now is convert our data into a spectrogram. But before we do that, we probably want to load up all of our data to get ready to actually build our deep learning model. And to do that, we're going to be using the Tensorflow Dataset library. So this is really, really good because it actually allows you to build a data pipeline when you're loading in significant amounts of data. So it's good if you don't have too much memory on your computer. It's good to actually do that pre-processing for you. So the first thing that we're going to do is we are going to define 2 paths to our positive and our negative data. So these are really just file paths. So I've called the first one, so pos equals to os.path.join. And the first file path is going to be data, and the second directory that we need to go into is past_capuchinbird_clips. Then we've defined a negative path, or where our negative examples are. So neg equals os.path.join. And then we're going into our data folder again, and then we're going to be going into past_not_capuchinbird_clips. So if we go and run that, and again, these are just file paths, right? So if I type in pos, that is just our file path for our Capuchinbird clips, which is effectively this. We go into neg, that is the file path for our past not Capuchinbird clips, which is going to be this one. Cool. All right, those are our 2 file paths now defined. Now, the next thing that we want to do is we actually want to load it into the TensorFlow datasets format. So in order to do this, we're going to be using the list files method. So this effectively is going to give us a set of files as a string inside of a TensorFlow dataset format, and then we'll actually be able to pre-process these and load them up. So if we go and run these now, that looks like it's run successfully. So let's take a quick look at what we've written there. So pos equals tf.data.dataset, and then we're going and using that list files method. And this really just goes into a directory and looks for files of a specific format. Now we are telling it to go into the positive directory here from up there, and we're telling it to look for anything that ends in .wav because those are going to be our audio files. And we've done a similar thing for our negative examples, except the only difference is we're going to be going into our negative folder, but again, looking for files that end in .wav. Now, what we can actually do is we can actually take a look at one of these examples. So if I type in pos.asNumPy_iterator.next, that is what our TensorFlow dataset currently has. So it's got a string or a string path to a specific file. So it's got data and then past_Capuchinbird clips, and then the file that it's returned back in this particular case is xc27882-1.wav. So it doesn't actually have the audio file at the moment. It just has the file name or the path to the file. What we'll eventually do is we're going to use the map function from the TensorFlow dataset method or API, and we're actually going to run our load wave _16k mono function on that, or on each one of those file paths. So this is actually going to allow us to load in our specific file. Cool. So right now we've got a big list of all of our different files that we want to work with, and we've got the positive and negative examples. But the next thing that we need to do is we actually need to give it some labels, because right now it's just the file. We don't know what's a positive example, so i.e. a capuchin bird, versus a negative example, i.e. not a capuchin bird. And that is exactly what we're doing here. So again, we're using the TensorFlow dataset method, so tf.data.dataset.zip. So this allows you to concatenate 2 different files together, but it's actually going to concatenate them in line. And we are passing through our existing file paths, but we are going to be adding through a positive 1 if it's a positive sample, or a 0 if it's a negative sample. So to do that, I've written tf.data.dataset.from tensor slices, and we are appending tf1s of the same shape as our different files. So this is effectively going to return back. So let's actually take a look. So if we type in len pos, we've got 217 different files for our positive examples. If we then go and pass that to tf.ones, we're going to get a big tensor back with a whole bunch of ones. So this effectively means that each one of our files that is a capuchin bird, we are going to be passing through a 1 binary flag to say that, yes, this is in fact a capuchin bird. So it's going to be a binary classification problem at the end. And we've done a similar thing, but for our negative examples, we're using tf.0. So this, rather than having the 1s, we're going to have 0s. So if we go and run that, So it's going to be TF zeros for our negative examples. And it looks like we've got 593 samples. So this is an unbalanced data set. So ideally what you might want to do later on to improve performance is to balance this out. So effectively resample or undersample your negatives. Cool. All right. So that is those two lines there. So we're going to take a look at that. So let's actually run this. So if we go and take a look at our positives, first up, positives, and we're going to use as numpy iterator again, dot next. What we've actually got now is no longer just a string, we've also got the flag. So in this particular case, this particular file is an example of a capuchin bird, hence we've got the binary flag 1. If we went and did the same thing for our negatives, again, we've just got the file path to our negative example, but we've got a 0 binary flag. Cool, cool. Now, we probably want to join all of these together, and this is where the next line comes in. So what we're going to do is we're going to concatenate all of these together. So we're going to effectively have our positive, negative, or have our positive examples and our negative examples in the same variable. So we've specified data equals positives dot concatenate negatives. So this is just going to bring it all together. The file structure or the shape of the result is not going to change at all. So if we actually go and take a look at data, exactly the same, right? But now we're going to have our negative examples and our positive examples in the exact same format. So if I actually went and typed in dot shuffle and passed through 10,000, for example, and we need to shuffle it first. Right, so here we've got a negative example, run it again, negative example, negative, 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 give me a positive one. Let's change this. That's a positive one, negative one, positive one, positive one, positive, negative. So you can see that we've now got all of our data stored inside of this one data pipeline. So this data variable is what we're effectively going to be using later on to work with or when it actually comes to train our deep learning model. Alrighty, cool. Let's bring that down there. So this is part 3 now done. So we've gone and defined our paths to our positive and negative data. We've gone and created our TensorFlow data sets. We've also added our labels and combined our positive and negative samples. Now, the next thing that we probably want to do is determine the average length of a capuchin bird call. So a little bit of exploratory data analysis. And this is important because when it comes to converting our spectrogram, we want to ensure that we capture what is effectively a full capuchin bird call, or at least the majority of it, so that when we go and slice through our bigger clip, we're capturing the entire call or the majority of it to ensure that we have good predictions. So what we can do is we can go and loop through every file that we've got inside of our past capuchin bird clips file and calculate how long it actually is. Now, in order to do this, we're going to create a new variable called lengths, and it's just going to be a blank array. We're then going to loop through every file inside of our past capuchin bird clips folder. So I'm just using os.path.join to get the folder path, and then we're using os.listdir to get every single file. So if I actually show you what this does, so we're just going to get a set of files that are inside of that folder, right? Then we can loop through each one of them and use our load_wave_16k mono to load up our file into its waveform. And then what we're going to do is we're going to get the waveform back. So this is going to be the 16k equivalent. We can then take a look at how long each one individually is, because they're not all going to be 3 seconds. Some might be longer, some might be shorter. So we want to at least ensure that we capture the majority of the wave in that particular form of classification. So if we go and run this, it might take a little while to run, and you can just ignore that error. That's perfectly fine. Once we've got that back, we should effectively be able to calculate the mean, min, and max. So that's now done. So we can actually take a look at our lengths. So you can see that we've got a whole bunch of differing variable lengths or file lengths in this particular case. So some of them are 40,000 time steps long, some of them are 48,000. So they're varying, right? And this is important to note because let's say that the capuchin bird call is really short or was really, really short. Then you want to effectively capture each one of those calls. Now, let's actually take a look at some summary stats on this. So if we actually go and calculate our mean, it looks like our median call length is 54,156 values. So in this particular case, it means that each one because we've got 16 hertz. So what does that actually calculate down to? Pulling out my phone. So if that means we've got 16,000 cycles per second. So if we divide 54,156 by 16,000, so that means on average, our capuchin bird call clips are about 3.3 seconds in this particular case. So we're probably going to want something that captures the majority of this. Now, it probably doesn't need to be 54,156. We can capture the majority, let's say 48 or something along those lines. But let's take a look at some other summary stats. So we can take a look at our min. Our min is about 32,000. What's our max? And our max is about 80,000. So we'll play it safe and we'll probably just grab around about 48,000. But again, you could definitely tune this if you wanted to grab more. Just keep in mind, the larger you make your spectrogram, the more variables you're going to have in your deep learning model, which means the more time it's going to take to train, which means the higher latency that you're going to have. So ideally, you want it to be quick when you're processing, but just that's something to keep in mind. Cool. So we've now gone and taken a look at some of our summary statistics for our audio. So we've gone and taken a look at our average length of each one of those calls. So that means our shortest one is going to be 32,000, which is going to be about 2 seconds. Longest one is going to be 80,000, which is about 5 seconds. So they're between 2 seconds and 5 seconds in length. Okay, so we've now gone and done that. So we've got a little bit of information on our average length of a capuchin bird call. The next thing that we want to do is actually get to what we promised Damone that we do. We want to convert our data into a spectrogram. And in order to do this, we are going to be using Tensorflow. So we're going to be using the short time Fourier transform to convert it into a spectrogram. Now, this is the function that we're going to use. So it's called preprocess. And to that, we are going to be passing through our file path and our label. Now, you're probably thinking, Nick, why do I need to pass through the label to create a spectrogram? Well, that's because we are actually going to be using this specific method as part of our data pipeline, which we defined. Where is it? Right up here. Now, when we actually use the map method on this, it's expecting, or it's actually going to pass through the full sample. That means it's going to be passing through the text and it's going to be passing through the label. Now, we're not actually going to do anything with the label in here, but we want to ensure that we take it in and we return it back at the end. Okay, so what is this actually going to do? Well, our preprocess method is first up going to load our data into its waveform. Remember that function that we wrote up at the start? So load underscore wave underscore 16K mono. We're then going to grab the first 48,000 steps or examples from each one of those signals. Because in this particular case, you could bump it up. You could make it 32. It's probably a little bit short. You could make it 80, but just keep in mind that's going to be more data that you need to process. So in this particular case, let's try at 48K and go from there. But not every single one of our clips is going to meet that specific limit. Because remember that some of our clips are 32,000 examples in length. Now, how do we actually handle this? Well, what we can do is we can pad it with 0. So anything that doesn't meet the full length of a clip, we can actually use tf.zeros and pad the rest. So what we're going to do is we're going to take any clips which are shorter than 48,000 examples or samples, and we're just going to throw zeros out at the front. So say, for example, it was 32,000 zeros in length, then what we're going to do is add, what is that? So 16,000 zeros right at the start of it to effectively ensure that all of our clips meet that 48,000 sample length. So this is everything that is doing here. So we're using tf.zeros, we're passing 48,000 and we're subtracting the length of the actual wave file. And then that is going to give us the number of zeros that we need to add at the start. And then we're grabbing the wave file and we're overriding it using the tf.concat method. So we're going to append or concatenate all of the zeros at the start plus the actual wave file. And that is going to give us our final file that we're then going to use to create a spectrogram. Cool. This brings us to our spectrogram. So in order to create a spectrogram, we're going to use tf.signal.stft, which gives us our short time Fourier transform. To that, we're going to be passing through our wave file. We're going to be specifying our frame length, which is 320, and our frame step, which is 32. So this is the sample rate, I believe. We're then going to convert it into an absolute set of values. So we're going to, everything's going to become in its absolute format. So we're going to get rid of the negatives. Everything will become a positive example. we're then going to expand our dim. So this is going to encapsulate our spectrogram in another set of arrays to ensure we have it in the appropriate format that we need to go and produce a deep learning model. So let's actually take a look at this and I'll step through it. So let's grab our first file path. And let's pass through the capuchin bird call. Right, so that's our wave file. So it's just a set of tensors, 48,000 steps in length. Then let's go and apply our zero padding. Well, this one's 48,000, so you're not going to see any change there, right? So if we go and paste that, it's going to be the exact same thing. Take a look at our wave. Again, 48,000. There's no zeros at the start because that meets the minimum length. We're then going to create the spectrogram. So if we go and do that. So our spectrogram is currently in the format of 1,491 and 257. Well, it's 1,491 by 257. So that is the shape of our spectrogram. Now by adding this, or we're going to absolute it as well. So let's do that first. But I want to explain that expand dims bit. So again, no change in the format. Rather, all we're doing now is we're absoluting or converting it into an absolute set of values. So if we actually comment that out, so you can see that we do have some negatives there now. Go and apply the absolute function, tf.absolute or tf.abs. We no longer had negatives. Now, the expand dims function is then going to give us this a set of channels. So it should become 1,491 by 257 by 1. And this is needed so we can use our convolutional neural network on it because it's expecting a channels dimension. So if we go and grab this, boom, it's now by 1, right? So this is almost like you were processing a grayscaled image. That is effectively what you've got on your hands here. So with any other image, you'd probably have X by, or height by width by a specific channel. And normally if you've got a color image, it's going to be 3 channels, so RGB or BGR. In this case, we only have a single channel. But that is our data or our waveform now converted into a spectrogram. But you're probably thinking, Nick, what does this spectrogram actually look like? So let's actually take a look. So let's test out our function first up. So we're going to grab a sample out of our positives data or data pipeline. So we can go and run that. And to do that, I've just run positives.shuffle buffer size equals to 10,000. So you've probably seen me write this a little bit earlier, just up here. Really no different. And we've just run .as numpy iterator .next. So this allows us to get the next example out of our data pipeline. And what we're going to get back is our file path. And we're also going to get back our label. Because remember, we haven't done our pre-processing yet on our data pipeline. So if we go and run this now, we actually need to run our function. We are now going to have a spectrogram back. Spectrogram. So remember, it's in the same file format. So 1,491 pixels by 257 pixels by 1 channel. And now we can actually go and visualize it. So let's actually take a look at what this bad boy looks like. So if we go and run this, that is our spectrogram. So we've now taken our raw waveform and we've converted it into an image. So that is, if we actually go to visualize a capuchin bird, that is what it actually looks like. Now we could also take a look at a negative example. So let's change this from positives to negatives. So that's our spectrogram. We probably don't need to see this. Go run it. So that, in this particular case, that is what a negative example looks like. So very, very different, right? So our capuchin bird had that distinctive warbling. This is just almost looks like noise, right? We can then go and grab another example. So let's actually take this off and we can run file path, comma label equals this. Oh, actually, this should actually give us our next. Right, so that's another negative. That's another negative. It's another negative. It's another negative. We can jump back. Let's jump back to our positives. That's a positive. That's a positive. So are you sort of noticing a pattern there? So the capuchin bird call sort of stands off kind of low and then rises and then continues on. So that's sort of that warbling that you hear, right? And this is how cool is this, right? We've actually visualized what a capuchin bird sounds like. Now we can take a look at more, keep running this cell. You can see you've got that warbling, so it sort of starts off low and then rises up there. Pretty cool, right? Okay, so that is our spectrogram now created. So let's quickly take a look at what we've gone and done there. So we have first up, where did we start? We were up here. So we've first up gone and taken a look at our positive and negative data. So we've gone and created our file paths. We've gone and created our Tensorflow data sets and added our positive and negative labels to them. We've then gone and determined the average call length, so we know how much of the call we actually need to capture, and we've decided on about 48,000 examples. So let's scroll on down. We've got the 48,000. Anything that doesn't meet the 48,000, we're just going to pad it with zeros at the start. Then we've actually gone and converted it into a spectrogram using the tensorflow.signal.stft method. And that is what you get there. Now, I didn't actually talk about this, how we actually visualize this. So we've just gone and used matplotlib. So plot.figure, and we've passed through fig size, and we've set that equal to 30 by 20. And then we can use plot.imshow, and I've just transposed it in this case, so you can sort of see it across the time. So tf.transpose, and we're passing through our spectrogram. And that is what you see there. Let's jump back over to Damone and give him an update on our spectrograms.
So spectrograms are now done. What's next? We're pretty keen to get this done. Well, thankfully we're now up to the modeling stage. We'll now build a deep learning model to detect single capuchin monkey calls. But how's that going to help with detecting call density? Well, once we've got this model trained, we'll actually slice up the longer clips of the forest into shorter windows. We can then use that model to classify if there's a capuchin heard in that specific clip or not. Ah, right. So then you can aggregate the results and calculate how many calls were heard? Exactly. Let me jump back into it.
Alrighty, so we've done a lot of pre-processing, but we haven't necessarily done a lot of deep learning, and this is where it's going to kick in. So the first thing that we need to do is actually create a training and testing partition. Now, in order to do this, we actually need to go and finish off our TensorFlow data pipeline, because up until now, remember that our data pipeline, which is stored inside of data, so if we go run data.asNumPy iterator, this is still only currently holding the string or the file path to our audio file and the label. We haven't actually run it through our spectrogram method yet. So that's exactly what we're going to go on ahead and do. So in order to do that, we are going to mkshabap it. So this is the way that I actually remember how to go and pre-process TensorFlow data pipelines. So first up, we are going to map it, then we're going to cache, so mk, and then we're going to shuffle it, then batch it, then prefetch it. Shabap. I don't know if that's all I could come up with in terms of creating my memory palace. So, all right. So remember, our data pipeline is just a string at the moment. So we are first up going to specify data equals data.map, and this is going to run it through our spectrogram method, which is up here. So remember, pre-process takes in a file path and a label, outputs a spectrogram and a label. So first up, we're going to run it through map, then we're going to cache it, then we're going to shuffle it. So this is going to mix up all of our training samples. So rather than just having positives at the start and negatives at the end, we're going to have a mixed bag. So this ensures that we're not going to necessarily overfit, and we're going to introduce unnecessary bias or variance into our model. Then we are going to batch it up. So we are going to train on 16 samples at a time, and then we're going to prefetch. So we're going to specifically prefetch 8 examples. So this eliminates any CPU bottlenecking. Cool. So that is our TensorFlow data pipeline. So let's run that. Cool. So that is our pipeline now built. Now we're going to split it into training and testing. So again, this is good data pre-processing processes. So what we can do is run data.take, and we're going to grab 36. So if we take a look at the length of our data, right? So it's 51 samples. So let's say we take 70% for our training partition. So that should be around about 35.7. So we're going to round that up and take 36. So then what we can do is assign that partition to train. So train equals data.take 36. And then we're going to skip those 36 and take the last 15 as our testing sample. So this is effectively going to give us our training and testing partition. So if we run that, that is now done. Now what we can do is test it out. So let's grab a training example. And again, as per usual, we're just using the asNumPy iterator generator and grabbing the next sample. If we take a look at our samples.shape, we're now going to have 16 different examples of our spectrogram, which have the shape of 1491 by 257 by 1. This is really important because we're going to need this specific shape to pass through as our input to our deep learning model. But for now, that is that bit now done. So we've now gone and created a training and testing partition. So we've gone and built up we've gone and finalized our TensorFlow data pipeline. So we went and ran it through the Mixshabat pipeline. We then went and created a training and testing partition. So we took the top 36 as our training sample. We then skipped those 36 and took the last 15 as our testing partition. Then we've gone and tested it out in one batch, and you can see that we are definitely returning back our spectrogram now. We can also take a look at our labels. So our labels are just our ones and our zeros in this particular case. Okay, now the next thing that we actually want to do is actually build our deep learning model. So in order to do this, we are going to need a couple of dependencies. So specifically, we're going to need the sequential API because we're just going to build a sequential model, no fancy inputs here. And then we are going to bring in 3 different types of layers. So we're going to bring the conv2D layer, the dense layer or fully connected layer, and the flattened layer to go from a convolutional layer to a dense layer. So to do that, we've written from tensorflow.keras.models import sequential. And then to bring in our layers from tensorflow.keras.layers import conv2D dense and flatten. I was just thinking about how I actually remember layers, and I always think of Donkey from Shrek talking about the onion. But anyway, that's how I remember layers. Okay, so those are the 2 different layers that we're going to need. So sequential, conv2D dense, and flatten. Now we can actually build up our sequential model. So let's take a look at this. So first up, we define our sequential model. So model equals sequential. So we're instantiating an instance of this class. Then we're adding a bunch of convolutional layers. So the first one, we are running model.add, and then we're passing through conv2D here, which is there. So conv2D, we're specifying that we want 16 different kernels of shape 3x3. We are not updating the stride, so we're just leaving that as its default. We're specifying that we want an activation of a ReLU function or rectified linear unit. And then we want our input shape to match what our spectrogram looks like. Because remember, this is why I said it's important. So if we go to samples.shape, our spectrogram is the shape 1491 by 257 by 1, 1491, 257 by 1. If you change the shape of your spectrogram, i.e. you go and change how big of a waveform you pass through to your spectrogram, or you actually change the parameters to create when you're actually using the short time Fourier transform over here, then you might need to actually go through and update that input shape. But using the parameters that I've gone and passed through, that'll be the input shape over here. Cool. So that's our conv2D layer. Then we're using another one almost identical. So conv2D 16 3x3 activation equals ReLU. And then we are flattening it down. So we take our convolutional outputs, which are going to be in 3 dimensions, and we flatten it down to a single dimension. And then we pass that to our dense layer, which is going to have 128 units and activation of ReLU. And then that final layer goes to our final layer, which is going to be a dense layer of 1 value, because it's just going to output 0 or 1, because we have gone and specified an activation of sigmoid. Cool. So if we run that, that's going to create your sequential model. Cool. So no errors there. Now we can compile it. And to compile it, we're going to be using the atom loss or the atom optimizer with a loss of binary cross entropy, because really this is just binary classification at the moment. And then we're actually going to pass through a couple of metrics. So we are going to specify metrics equals, and inside of a list, we're going to specify tf.keras.metrics.recall. So this is going to give us our recall metric. And we're also going to specify tf.keras.metrics.precision. And that is going to be inside of model.compile. So that will compile our model, and then we can take a look at it by running model.summary. And that is our neural network. So again, this is pretty big at the moment. So we could actually compile this down, maybe do some max pooling or something. I've found that this tends to work, but it is very big. So it's got 770 million parameters in it. So quite a bit of a monster. But again, you could definitely narrow this down. So drop in a couple of max pooling layers between here and between here. But in this case, this tends to work. Cool. So that is our deep learning model now created. So remember, we've gone and specified our sequential model, added our convolutional layers, flattened it, and then added our dense layers. And then we compiled it and took a look at our summary. Cool. That is that now done. Now what we can do is actually go on ahead and train it. So in order to train it, we can specify hist. So this is going to allow us to get the training values and specifically the loss metrics for our validation partition and our training partition. And we will also get our different metrics as well. So by capturing this memory, you'll actually be able to visualize it, which I'll show you how to do in a sec. So hist equals model.fit. We're going to pass through our training partition. Specify we want to train for 4 epochs. You could train for a longer time. You could train for a shorter time, depending on how accurate you want your model to be, and also based on whether or not you're starting to overfit or not. And then we're specifying validation data equals test, because that's going to be our validation partition. Cool. So if we actually go and run this now, this should effectively kick off our training. So we'll give that a second just to ensure that it's kicked off successfully. That's working. So you can see that our model is now training. That is what this line down here represents. And ideally, you should start to see this loss reduce, our recall increase, and our precision increase over time. So let's let that run for a little bit. Alrighty, so we've now gone and successfully trained our audio classification model. So you can see that after 4 epochs, we've got a pretty good model. And I mean, I'm always skeptical whenever I get 100% on anything. But on our training partition, we do have a 100% recall and 100% precision. Likewise on our validation partition. So it's looking pretty good in this particular case. Ideally, you'd want to bump up more data and probably flesh this out, but we'll eventually see how this actually performs on the final model. Let's actually take a look at some plots. So if we take a look at our loss, it looks like it went pretty much down and sort of stayed down. We take a look at our precision, sort of trended towards upwards. Doesn't look like we've got any overfitting there. And likewise, we can take a look at our recall. Looking pretty good. So in order to run these plots, so I've just set the title. So matplotlib allows us to do that. So plot.title, and we've set it equal to loss. And then remember, this is the advantage of saving your history or the memory. So if we go to hist, you're actually going to get back a whole bunch of values if you go to .history. So you actually get your loss, your recall, precision, validation loss, validation recall, and validation precision. And you'll get each one of these per epoch. So it's actually pretty cool in that sense that you can grab all these values. In order to plot them, we can just run plot.plot and grab the specific metric that we want. So in this first plot, I've gone and set loss equal to, or I've gone and passed through loss first, and I've set it equal to red by passing through the color code. So plot.plot hist.history, so that grabs this value. And we specifically want this metric here because it's a dictionary. So if we go to type, it's a dictionary, so we can grab the specific metric that we want. Loss. And these values are effectively what we're going to be passing through to this plot. And we're setting it to red. Likewise, we can do it for validation loss. I've just gone and done pretty much the same thing there, except we're grabbing val loss. Pretty cool, right? And so I've just gone and set basic loss to red and validation loss to blue. Likewise, I've done the exact same thing for precision and recall. So we're grabbing precision and validation precision, recall and validation recall. But that is actually looking pretty good right now. So after only 4 epochs, we've got pretty much 100% recall, 100% precision. Haven't done too much data transformations or data augmentation, but you could definitely add that as well if you're getting less than better performance. Okay, so now that that's done, the next thing that we actually want to do is make a prediction. So we're going to grab one batch out of our sample or our test sample. And to do that, I've just written test.asNumPy iterator, and I've grabbed the next batch. Out of this, we're going to get our spectrograms, and we're also going to grab our labels. So if we go and run this, xtest should be 16 spectrograms. So if we take a look at the shape, right, so 16 spectrograms by 1491 by 257 by 1. Cool. Y-test should be 16 labels. Cool. So we've got 16 labels. Now we can actually pass through xtest to our model. So model.predict is going to allow us to pass through our audio clips to our deep learning model and make predictions. So if we go and run this now, boom, those are our predictions. And if we take a look at y-hat, these are our logits or our confidence metrics. So you can see that if we, right now we're just getting probabilities. So this looks like that is a capuchin clip, that is a capuchin clip, that is one. But rather than looking at this manually, we can really just convert these to classes. So if we go down here, what we're going to do is effectively just loop through each one of these predictions. So for prediction in y hat, if that particular prediction is above 50%, then we're going to set it equal to 1. If it's below, then we're going to set it to 0. So this is just a Pythonic way of writing it. Really, all I'm doing is I'm writing this for prediction in y hat if prediction equals or is greater than 0.5. What are we going to do? So let's actually create an array. So y hat equals array or blank array. And then we are going to be setting y hat dot append 1, else y hat dot append 0. That is effectively all we're doing. But writing it like this is much more Pythonic and allows you to skip doing all of that or writing this many lines of code. So if I go and run this now and take a look at y hat, boom, those are our results. Pretty cool, right? Now we could also take a look at our actual results, which is what we'd get from y test. So here it looks like we've got, do we have numpy? So tf.math.reduceSum. So let's have a look at how many capuchins were heard in that clip. So it looks like 5 capuchins were heard in that clip. So if we go and take a look at our actuals, so tf.math.reduceSum and take a look at y test, 5 capuchins. How good is that? So it looks like we're accurately predicting, right? But let's actually take a look at the classes. All right, okay. We can convert this dot as type int. All right, so we've got 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, so 4 zeros, 1, 2, 3, 4, 1, 0. How good is that? So we are very accurately predicting where we're hearing capuchin birds. We can take a look at another sample. So run this again, make some more predictions, run through our classes again. So again, 1, 1, 0, 0, 0, so 4 zeros, 1, 1, 0. So we are accurately predicting what is a capuchin and what is not. So that is already performing really, really well. And keep in mind what we're passing through when we pass through X test is we're actually passing through the spectrograms for each one of those original capuchin clips that we're getting in part of our training and testing partition. So it's performing very, very well in this particular case. Now, on that note, let's jump back over to our client and have a quick chat about how our model is actually performing.
Simone, we can knock off the deep learning model from the Kanban board. It's done and it's performing pretty well. We're getting well into the high 90s for both precision and recall. A higher number is better, right? Right. The higher precision and recall, the better we're going to be able to find those capuchins. All we have to do now is slide the model across the longer clips and aggregate the number of calls heard. So after this, we'll have density counts. Bang on, let me wrap it up.
All right, time to start going through our forest clips. So remember when we actually went and worked or took a look at our data right up at the start, we had 3 different folders. Actually, we don't even need to go into here. So we had 3 different folders. So if we go into our data folder, we had forest recordings, past capuchin clips, and past not capuchin bird clips. But we've only worked with these 2 folders at the moment. We actually need to get into our forest recordings and start dealing with these. And these were around about 3 minutes long as opposed to being 3 to 5 seconds or 2 to 5 seconds. Remember, that was the min and max length when we took a look at each one of our different capuchin bird training samples. So what we actually need to do is first up, load up our MP3s because these are no longer WAV files, right? You can see that they're MP3s over there. So we're going to need to load those. So let's do exactly that. So what I've gone and done is I've gone and tweaked the load WAV 16K mono script and done a little bit of tweaking to get this to work. So rather than using the tf.io.loadWave method, we're going to use this one. So tfio.audio.audioio tensor. So this is actually going to take our MP3 file and still convert it into a tensor. But each one of those files are actually multi-channel. So rather than just dropping one channel, we're actually going to take that tensor and we're going to add them together and divide it by 2. So we're going to take the average between the 2 different channels to reduce it to a single channel value. And that is exactly what we're doing there. And then pretty much the rest of this is exactly the same as what we had during our initial 16K load up method, right? So if we go and run this now, what we can then do is grab one recording. So mp3 equals os.path.join, and we're going to go into the data folder, which is this. We're going to go into forest recordings, which is this, and we're going to grab the first recording. So recording underscore 00.mp3. So let's do that. So that is defining our file path. We can then load it using our loading method there. And now what we're going to do is something a little bit trickier. So we are going to convert this big file into a number of audio slices. So rather than just taking one massive clip and trying to make a prediction, we're actually going to slice this up into this same size audio slices that we'd pass to our model. So this means that we're actually going to perform multiple predictions on a single audio clip. So if we go and run this line here, this is going to do exactly that. It's actually going to give us those different slices. So by running tf.keras.utils.timeseries_dataset from array, that is going to give us our different slices of that longer clip, right? Got a little bit tongue-tied there. To that, we are going to pass through a WAV file. So if I go and show you that, exactly the same as what we had during our smaller clips, it is just much longer there. So to this keras method, we are going to be passing through this WAV file from over here. I'm going to be passing through that a second time. So this passes through the input and the target. We then go and pass through how long we want our sequences to be. And remember, we set it to 48,000 samples. Our sequence stride is going to be 48,000 as well. So rather than having overlapped sequences, we're actually just going to take non-overlapping sequences. So by specifying our sequence stride equal to the same length as our sequence length, they're not going to overlap, and we're only going to have one batch from this as well. So if we go and run that, we are going to then have our audio slices. So if we now go and take a look at samples.shape, we now have one. In this case, our batch size is only one, so you're only going to get one. But if we actually take a look at the length of our samples or length of audio slices, what we've actually done is we've taken one full clip and we've actually converted it into 60 different windows. We're then going to take those windows and actually convert them to spectrograms, and then we'll be able to loop through them all and make predictions. So let's actually convert them to spectrograms. Again, pretty much the same function. We're just going to be squeezing the dimensions because this has a channel at the start. And then this, everything that you sort of see here is exactly the same as what we had during our initial spectrogram pre-processing method. So if we run this, and then let's actually go and convert our audio slice into those spectrograms. And now if we make predictions, let's actually run through this. This is actually going to make 60 different predictions. So if we go and type in y-hat now, you can see we've got all of these predictions, right? So if let's actually take a look at the length of this. Should be 60 or 180. Why do we have 180? Are we taking a look at multiples? This should be different. This is not 16,000. This should be 48,000. Let's change that up. Now if we go and make our predictions, right, 60, cool. Now if we take a look at these predictions though, what you'll notice is that we've got consecutive predictions. Let's actually go and take a look at our first example as well though. So it is recording underscore 0.mp3. So let's actually go and play that file so we can hear it. Recording 0. So let's do a manual count. So that's 1. That's 2. My hand's getting tired holding it up. That's 3. That's 4. And remember, our model predicted 5 for this particular clip. That's 5. Okay, let's wait and listen to all the way to the end just to ensure there's no other detections or no other calls that we've maybe missed. Nope. Okay, so there weren't actually any other detections. So it's accurately predicted 5. Now, the only thing that you'll note is that when we go and take a look at those predictions, is that it's classifying consecutive calls as additional predictions. So what we actually want to do is reduce this down. So consecutive calls are only treated as a single call. Now, we can actually do this using the group by method out of the iter library. So we're going to do exactly that. But let's actually go and take a look at how we might go about doing this. So if we go and import the group by method, so from iter tools, import group by. And then what we're going to do is we're going to loop through the predictions from y hat. So exactly what we had over here. And we're going to reduce the sum. So let's actually take a look at the reduced values first. So if we go and take a look at y hat now, we have 1, 2, 3, 4. Wait, hold on. Are we looking at the right thing here? Model.predict. Run through that again. We've got 1, 2, 3, 4. Oh, wait, we've got a whole bunch of additional predictions after this. Hold on, I realize what we're doing wrong. So what we can do is we can increase the confidence of our model. So rather than leaving a prediction over 50% as a valid capuchin call or capuchin bird call, let's bump this up to 99. So this means that we're only going to take the most confident predictions as being valid call detection. So if we now go and run through y hat, this means that we are going to have, let's take a look. So we've got 1 there. We've got 1 there, assuming we group that together. So that's 2, 3, 4, and then 5. So that means we've effectively detected them successfully. So rather than leaving in the lower confidence detections, which may be lower than 99, we're only going to take the most high ones in this particular case. So if we actually go and run through this now, so if we go and sum this up, so np.sum, oh, we don't have numpy imported, so tf.math.reduce sum. Right, so we've now got those 5 detections. If we drop this lower, let's take a look at the result that we get. So if we go and drop that confidence metric, or effectively our threshold, y hat should take in more detections. So we're going to get a lot more sort of bubbling at the end. And now if we go and run through this, we're now detecting 11, which in our particular case, we know is not right. We only heard 5 capuchin bird calls. So let's make it really confident and bump up that threshold to 0.999 or 0.99. Again, enable scrolling for this. And if we go and take a look at those final results now, loop through them, we've now got those 5 detections. So it looks like we're performing a lot better in that particular case. And that is effectively what we were aiming for, right? We were aiming to get the number of calls per forest recording. But now what we actually need to do is loop through every single one of our files within this forest recordings directory. So rather than, we can run this as well. It's the exact same as what I've just written here. So this tells us that we've got 5 calls. Now what we can do is loop through each one of those. So we are going to do a similar thing to what we did when we were calculating the call length. So we're going to loop through every single recording in the forest recordings directory. So for each recording, we're going to load it through the MP316K mono pre-processing method. We're then going to convert it into the audio slices, and our stride is going to be, or our sequence length is going to be 48,000. Sequence stride is going to be 48,000. We're then going to perform our audio pre-processing to convert it into a spectrogram. We're going to batch it up and then make some predictions. And then what we'll do is we'll convert it into classes. We'll use our 0.99 detection threshold and we'll go through there. But for now, let's go on ahead and run this on all of our detections. It will take a little bit of time, but if you run this, this is going to go on ahead and make predictions over every single one of those recordings inside of that forest recordings file. So we'll let that run and we'll be back in a second.
5 minutes later.
Alrighty, so those are our predictions now made, and they are going to be stored inside of a file called results. So if we go and take a look at that, you can see that for every single recording, so you can see that this is recording _00.mp3, we've got a prediction for every set of slices in that particular audio file. You can see we've got a really strong prediction there. We've got a whole bunch of others. Let's keep scrolling through. Some crappy predictions. Doesn't look like there's too many in there. But interpreting it like this is a little bit of a pain. So rather than doing that, we can actually go and convert all of these predictions into classes. So again, exactly the same code as what we had from over here. So again, we're going to be using our threshold of 0.99. So we want it to be very confident in those results. So what we're going to do is we're just going to loop through every set of results that we've got inside of our results dictionary, and we're going to convert them into class predictions. So that's what we've got there. So now that rather than having each one of those individual percentage or confidence metrics, we've now got these values, or effectively our classes. Now, rather than leaving it there, we can again go and convert this into grouped consecutive detections. So in this particular case, for recording 00.mp3, we can see that we've got 5 capuchin bird calls. So maybe that's an indicator of, I don't know, medium density. Let's enable or disable scrolling. So recording 0, 5, recording 08, 19 calls heard there. Let's actually go and listen to that one. So if we go into YouTube audio classification, data, which one had a lot of detection? So 19 was in that. Oh. So that is obviously very high density. So let's go to recording 8. Recording 8. Let's play that one. We've got one already. Two. Three. 4. So this is obviously a very high density capuchin bird area. 5. 6. 7. 8. You sort of get the drill. So it's obviously detected that there are a lot of capuchin birds in that particular area. So in terms of what our client might be interested in, so that area is obviously very dense. What's another area that's very dense by the looks of it? So remember, we've got 100 files that we just went and processed. It looks like location 87 has quite a number, and location 98 has quite a number of capuchin birds. So they are the leading areas that they might want to look into. Now, let's jump back on over. We're going to discuss these results with our client, and then we might have one last task.
Hey, Damone, what's your email? nftguruforlife@hotmail.com. Really? Yeah. Alrighty then. Well, I've got those metrics. I'm just going to compile them for each recording, and then I'll shoot it to you as a CSV, and you should be good to go.
All right, so we promised we'd go and export these results to a CSV. So in order to do that, we are going to import the CSV library just by running import CSV. And then what we can do is we can go and export this as a CSV using that particular library. So we've just written with open results.csv. So that's going to be the name of our file. So we could actually just call it Capuchin bird results. And again, if you're doing this for another use case, you could just name it whatever you want here. So Capuchin bird underscore results.csv. We're going to set it that we want to write. So that is part of the open method, and a new line is going to be started as part of a new line. We're going to set that as f. So we'll be able to work with the file as the variable f. We then define our CSV writer. So writer equals csv.writer. We're going to be passing through our file and specify that our delimiter is going to be a comma. So every value is going to be delimited by a comma. We can then use writer.writeRow to write out the title of our CSV file. So recording and a Capuchin calls. And then what we're going to do is we're going to loop through our results file, what we had over here. So this post-process dictionary that we just created. Now, if for that we've written for key and comma value in postprocess.item. So we're going to get the key and value from this particular dictionary. And we're just going to use writer.writeRow to write out the key and the value. So if we go and run this, we should now have a file called results.csv. And you can see that there. So that is our final set of results. So we've got our recording file name, and we've also got the number of calls. So in this particular case, recording 8 had a ton of calls. What's another one? Looks like recording 39 had 14. That's quite a fair few. Recording 61, 14 again. Recording 87, 24. Recording 98, 23. So quite a lot of calls in specific locations. But on that note, that does about wrap it up. So we've successfully gone and determined how many Capuchin bird calls are in specific areas. Now, again, all this code is going to be available via the GitHub repository mentioned in the description below. And once you've gone and calculated your results, be sure to jump over to the Unlocked with Z webpage and go on ahead and load up your results when you submit your answer here to enter the competition. But on that note, thanks again for tuning in, guys. Peace.
Thanks so much for tuning in, guys. Hopefully you enjoyed this video. If you did, be sure to give it a big thumbs up, hit subscribe and tick that bell, and let me know what you thought in the comments. How'd you go? Did you improve on the challenge? Did you beat it? How'd you go with your submission? Did you find anything interesting along the way? Let me know in the comments below. Thanks again for tuning in. Peace.